In this video, we are going to focus on 5.2, analyzing triangles. We've been talking about the Pythagorean theorem. We're going to continue using the Pythagorean theorem here. It's not going away anytime soon. Now, we're going to be looking more specifically at equilateral triangles to begin with, and then we're going to be looking at triangles with different angle measurements. So look, this is an equilateral triangle. Now, an equilateral triangle, make sure you have this in your notes, is a triangle with equal sides, because the term lateral literally means to the side or the side of, and equal means, well, equal. So all of these sides here are the same. So when we deal with these equilateral triangles, keep that in mind, they are all the same. Now, what does that say about the angles of the equilateral triangles? Well, the angles in any triangle has to have 180. So every triangle has 180 angles in it. So if we know that all the sides are the same, then also the angles have to all be the same. And so in an equilateral triangle, we have to divide that up into 3 equal parts. So each angle is 60 degrees. So in your notes, draw an equilateral triangle where all the sides are the same and each angle is 60 degrees. That's very important as we move on. And we're also going to be studying, okay, we know all of those angles are 60 degrees, but what if we draw this midline right here and that creates right triangles down here? Now, what do we know about some of these angles? What do we know about these side lengths? That's what we're going to be looking at to begin with in this section. So for this first part, I know that you have a lab sheet. You can look at this on your lab sheet. That's just fine. But you're going to be finding the angle measures and the lengths of all of those different parts of that equilateral triangle. So let's take a look at the lab sheet and answer number 1. Here's our lab sheet. And on number 1, so we're going to do number 1 on this one, on part A. And we're looking for angle CAP. So angle CAP, let's go ahead and put that there. Now, angle CAP, to figure out what angle that is, we just go from C to A to P. And the angle is that middle number, so this is the angle right there that we're looking at. And angle CAP, oh, sorry, did it wrong way here. So P is down here, my bad. C to A to P, not B. So it's actually this angle in there. Well, if we know that this angle is 60 and this cuts that in half, that means that this has to be 30 degrees. So you would say angle CAP is equal to 30 degrees. So the shortcut symbol for angle is just kind of a slanted L. So you could, on all of these, write it as angle CAP like that, 30 degrees. Now in number 2, they're looking for, so this is number 2, they're looking for angle BAP. So you would find that. And the easiest way is just to trace it. So B to A to P. And we would be looking for that angle right there. Let's see if I can't get this a straighter line. There we go. So we would be looking for that. Go ahead and do numbers 1 through 6 and then try number 7. On number 7, you can use one of these triangles or just draw another triangle down here. Go ahead and do numbers 1 through 7. 7's a little different than all of the other ones. So let's take a look at these. On number 1, we got that as 30 degrees. Make sure you're labeling just like this in your notes or on this lab sheets. Number 2, they want BAP, so that's angle A up here. And angle A, that also is 30 degrees. And then CPA, this is 90 degrees. And the next one is 90 degrees. And now these are side lengths. Now, the side lengths, in the beginning of the problem, they say the side lengths are 2. Okay, so in this one, the side lengths are 2, meaning this side length is 2, that side length is 2, that side length is 2, and so this is going to be half of 2, which is 1. Same thing for number 6, the side length of BP. Now, number 7, for the side length of AP, that's at height. This is right here. So I redrew it down here. We're trying to find that. Well, we know that this is 1. We know that this is 2. And we don't know what this is, right? So let's assign a variable. Let's say, well, that's one of the legs. So let's say this is B. We set up our Pythagorean theorem, right? So it's the legs squared together and added. So 1 squared plus b squared is equal to 2 squared. So it's 1 plus whatever b squared is equal to 4. Now we have to get b squared by itself. And when we're solving equations, in order to isolate this variable right here, we have to get rid of that 1. And so what you're going to do is you're going to subtract 1 from each side. And what we're left with, these cancel, and you're left with b squared is equal to 4 minus 1. That's 3. And to get b by itself, we have to take the square root of 3. So we know that b is just the square root of 3. Right, so then that would be the length of b would be the square root of 3. And that's AP. So we leave it as the square root of 3. You can find that as a decimal, but let's leave it as the square root of 3 for right now. So that answers all of 1 through 7 on that lab sheet. Now let's take a look at part B. We do not have a lab sheet here, but we're going to be using the same or similar triangles as what we used for the first one. They're all equilateral. Okay, they're equilateral, but now they have a side length of 4 units. So we're going through and finding those same things, but now if it's 4 units. So let's go back to our lab sheets. So to distinguish this from part A to part B, I'm going to use a different color for part B, because part A asks all of the same questions that part B is asking. The angle of CAP, the angle of BAP, so we're just going to keep this the same. All right, and you notice these two triangles, since they're both equilateral, they are similar to each other. Meaning, if you remember, the angles don't change. And so in part B, since the angles don't change, all of these angles are going to be the same. So 1 through 4, all of those angles will be the same as part A. What will change down here, now that this is 4, right, in part B, these side lengths are going to change. So let's look at that real quick. Okay, so since those side lengths change to 4, let's draw new triangles on a new sheet of paper here. So here's our triangle, and now these side lengths are 4. Okay, now to answer some of these questions, the length of CP and whatnot. So this is C, this is point C, this is point P, this is point B, and this is point A. And so CP is 1, or sorry, that's 2 now, and that's 2. Those answer the questions of those lengths, but now what we're trying to find, and I'll highlight it here, is we're trying to find that. So if I draw to the right, just that right triangle there, right, where that's 2 and that's 4, and let's say that that's B. Trying to figure out what B is, let's set up the Pythagorean theorem. So you'd have 2 squared plus B squared is equal to 4 squared. So that would be 4 plus b squared is equal to 16. And just like before, to get the b squared by itself, we're going to subtract away that 4 that's on the same side. So you'd have b squared is equal to 12. And to find b, you would find the square root of 12. And we're just going to leave it as that, the square root of 12. So when the side length's 4, b is the square root of 12. So that answers part B. Make sure you have that in your notes in a way that makes sense, because the relationship between parts A and B, the only difference is we doubled the side lengths from 2 to 4. Now let's take a look at those two triangles that we just did. Right, so this first triangle, this little one right here, I'll highlight in yellow. That was the triangle in part A, where this side length, this hypotenuse was 2, this was 1, and we found that to be the square root of 3. All right, so now let's take a look and compare that to the larger triangle. This is the one that we just did. We doubled the hypotenuse, and now this side length became 2, and that length, I'll write it in here, it's not in here, But that length, if you remember, was the square root of 12. But I guess we're not going to look at it that way because you notice that this right here, this point is halfway in between because this whole distance has to be 2. So from here to there has to be 2 units. So this is halfway in between. And so this is also 1. So the sides are going to be doubled here. So understanding that, and I just gave you some of this, but first of all, answer questions 1 and 2. Look at questions 1 and 2. Go ahead and try to answer those on your own. Some of them we've already answered, but try to answer them on your own and then come back to the video. Okay, on the first one, the triangles are similar. Are they similar? And explain how you know. In this case, yes, they are similar. If you remember back last year, we talked about similar figures, and these are called nestled similar figures or nestled triangles, where one is nestled inside of the other. So they are similar to each other. So yes, they are, because they are nestled triangles. And so, what is the length of a sub 2 to P? So what that is, I'll show you. So a sub 2 right here, P right there. So we're looking for that length. So one thing that you could do, if you remember what we did last year, is to set up a proportion from big triangle to small, or small to big, and so forth. So if we set up a proportion, so pause the video and try this if you haven't. Set up a proportion between the yellow highlighted and the blue or turquoise highlighted, and see if you can't figure out what from A2 to P is. So when we set up our proportion, let's go small, right? So the small hypotenuse is 2. The small leg is the square root of 3. So we'll go this leg over here. That has to be equivalent, because they're similar, to the large hypotenuse to the large leg. And let's say we don't know what that is. So that would be this distance from here to all the way down there, right? We did find that, but let's not use that, what we just did. Okay, we're going to go ahead and cross multiply, and we learned to do that last year. So you would have 4 times the square root of 3, because you would multiply the diagonals, is equal to, let's say the question mark is our unknown, so we'll put x in there, 2x. And now to solve for 2, we have to divide, or sorry, to solve for x, we have to divide out that 2. And when you do that, you get 4 radical 3 over 2. Those will simplify, and so you'd have 2 radical 3, and that is our length. So this length is 2 radical 3. So A sub 2 of P, that's 2 radical 3. C sub 2 to P, we said that was 2. Okay, so now the last question asks, hey, is this the same? Because we found that also to be the square root of 12. The last question on part 3 says, are these the same? Well, they look very different. When we plug them into our calculator, you get the exact same answer. So yes, they are the same, right? And the explanation is you can find the decimal of each one and compare them. So the decimal of each one of these is going to be 3.464. So 3.464. That's a rational number, so we use the approximation. An irrational number, so we use the approximation thing. So since the decimal is the same, they are the same value. Okay, let's look at part D. For part D, you have a lab sheet you can answer all of these on. So let's go ahead and jump over to that lab sheet to answer some of these questions. So the first question, so we have a 30, 60, 90 triangle, and it's a 30, 60, 90 triangle because those angles are 30, 60, 90. So 30, 60, 90. So that is a 30, 60, 90 triangle. Easy to identify if you can label those. Now, the reason we're using a 30, 60, 90 triangle here is because that is that portion of that equilateral triangle that we just studied, that we just looked at. So this is just the 1/2 side of it. So that's why we're looking at a 30, 60, 90 triangle. Now the first question says, what are the lengths of the other two sides? And in the problem it says the hypotenuse has a length of 10 units. Now the tricky part is they don't give us the lengths of any of the other ones. In all of these, we had to know the lengths of the other ones, but since this is a special case, there's a special relationship. Go back to part C to see if you can't figure out what is that relationship. Pull apart those 30, 60, 90 triangles that are similar, the smaller one and the larger one, see if you can't find a relationship amongst those side lengths. So think about that. Process it in your brain for at least 2 or 3 minutes. See if you can't try to come up with a relationship to find these other missing side lengths before you come back to the video and see what the answers are. Okay, so if we look at those other triangles first real quick from before. If you write them out like this, here are all of the side lengths, okay? It's also important to note that where the 30 and the 60 are. And the 90 is always across from the hypotenuse. When I say across from the hypotenuse, you take the hypotenuse and you go straight over, and that's your 90-degree angle. The 30-degree angle is always across from your shorter side. Like this side down here, this 2 is shorter than 2 square root of 3, it's always across from the shorter side. 60 degrees is always across from the highest or the biggest side. Because it's got that wider angle, right? It's going to have a longer side. So keeping that in mind, identifying where everything is, look for relationships. So if you haven't already, here are your triangles that we just did, found the side lengths, and again, this was square root of 12, but we're going to see a pattern easier if we write it as 2 square root of 3, which is the same thing as the square root of 12. So look for that pattern, see if you can't identify it to figure out, hey, what, given the hypotenuse of 10, what are my legs? Okay, spoiler warning, here it comes. So look at the relationships. Look at the relationship between the hypotenuse and the shorter leg. So this is your shorter leg. You notice every time the shorter leg is half the hypotenuse, right? So this leg right here, which is the shorter leg, always 1/2 whatever the hypotenuse is. So the shorter leg is always 1/2 the hypotenuse. And again, this is only for 30, 60, 90 triangles. Okay, for those equilateral triangles. And so knowing that that's true, here is our shorter leg right here. This is our shorter leg. And so this is going to be 1/2 of the hypotenuse, which is 1/2 of 10, which is 5. Okay, so this length must be 5 units. Now that we found that, we could do a squared plus b squared equals c squared, but let's look at the properties. Now let's take a look at the short leg compared to the longer leg. So you notice the shorter leg compared to the longer leg. Right, what's that relationship? Well, the longer leg, so this is the longer leg, and this is the longer leg. The longer leg is always 2 times, so 2 times the shorter leg. Sorry, not 2, but square root of 3. My bad. The square root of 3 times the shorter leg. Right, so in this case, the shorter leg was 2, and so the longer leg is going to be 2 times the square root of 3. Here, the shorter leg was 1, so it's going to be 1 times the square root of 3. So knowing that, right, if this is 5, the longer leg is going to be 5 times the square root of 3. Now, the cool part is we can always check that, right? You can do 5 square root of 3 squared plus 5 squared is equal to 10 squared. When you plug all of that in your calculator, you will end up with 100 is equal to 100. And you can go ahead and check that if you need to, but I know that it works. Now, part 2, we found the side lengths, explained how you found your answers, and we explained it by looking at the patterns down here. And then on number 2, it says, what relationships among the side lengths do you observe for this 30, 60, 90? And we already kind of talked about that. So on number 2, just kind of process that in sentence form, right? Process the fact that, hey, if you know the hypotenuse, it's really easy because the shorter leg is just half of the hypotenuse, and the longer leg is just the shorter leg times the square root of 3. Okay, that's if you know the hypotenuse. So go ahead and write that down in your notes, process it in your mind, and then write it out so that you can understand it in a different way. And then on number 3, so that was number 2 in part D. Number 3 says, if the hypotenuse is a 30, 60, 90 triangle, is S units long, what are the lengths? So this is huge, right? This is what all of this was leading up to. So I'm going to draw a right triangle. So let's say that this is our right triangle. So this is number 3. Okay, and let's say that this is 30, 60, 90. That's our 30, 60, 90. And it says, hey, if you know the hypotenuse is S, so let's say that that is S, what are the side lengths of the other ones? If you want to try this on your own, try it on your own. Pause the video and see if you can get this. Well, if we know the hypotenuse, we're going to start by the shorter side. And again, the shorter side is across from your 30-degree angle. So this is your shorter side that I'm pointing to right there. And your shorter side is whatever S is divided by 2. So it's whatever S is times 1/2. And then your longer side, which is across from your bigger angle, which is the 60-degree angle, that's always whatever this is, the shorter side, times the square root of 3. And that's it. So make sure this right here is in your notes and highlight that over and over and over again. Because in my life's philosophy, think smarter, not harder, this will make things a lot easier if you understand right triangles and the special right triangle 30, 60, 90 and the patterns of the sides. Now let's take a look at the last one, figure E. We're doing something similar, right? But now we're using those relationships and we're finding side lengths, which would be perimeters. And then part C, we're finding the area. So number 1, how many right triangles do you see? And there is a lab sheet, so I'm going to jump over to the lab sheet. But go ahead and try to answer part 1 for how many right triangles, and then 2, finding the perimeter, and then 3, finding the area of the triangle. So try these on your own and then come back to the video. Think about what we did. Think about how many right triangles are in there. You can draw them separately and divide them and use the fact that this is, remember, your 30-degree angle right there, okay? So also here, this is your 30-degree angle in here. So think of those things as you answer parts 2 and 3. So first, you should see 3 triangles. So number 1, there are 3 triangles. And all of those triangles are your 30, 60, 90 triangles. Every single one of them. Like if you look at this first one right here, that's a 30, 60, 90. The other one is right here. That's a 30, 60, 90. And the last one is right here. That is a 30, 60, 90 triangle. So for part 2, it says to find the perimeter, right? So to find the perimeter, let's look at the triangle that we know the most about. And that would be this triangle right here. Because for that triangle right there, we know that this is 30 degrees, this is 60 degrees, and this is 90 degrees. Okay, so what I'm going to do is I'm going to pull that out. So part of answering number 2. I'm going to pull that out, just redraw it down here because it could get messy up there. I know that this is 8. This is your 60-degree angle. This is your 30-degree angle. and we don't know what the other things are. But thinking about the relationships 30, 60, 90, if this is 8, well, I know that this is always half of the hypotenuse, right? And so if this is 8, the hypotenuse has to be 16. And if I know that then this is 8, this side has to be square root of 3 times 8, or 8 times the square root of 3. So let's go ahead and label the different parts that we find out up here, because we're asked to find the perimeter. So I know that this is 16, and this is 8 square root of 3. Okay, so that's our first triangle. So the next one that we could set up would be this one. This is our second triangle that we could set up. If we measure or label those parts, this is labeled as our 30, so that's our 60 degree. And we can find everything from that triangle. So let's go ahead and set this up down here. I'm going to just draw it separately. So this is your 30, that's your 60, you're right. And you know that this is the shorter side because it's across from the 30. Find the other side. So if you haven't done this, go ahead and do this on your own. So figure out what this side is, and then figure out what the hypotenuse has to be. Okay, so hopefully you did this on your own. The longer side length, remember the longer side length, which is this one, this is your longer length, that has a relationship with the shorter, where it's just the square root of 3 times the shorter side. And so for this one, since that's the longer side, it's going to be 8 times the square root of 3, which is just this, times then the square root of 3. And that will be that length. And then the hypotenuse is double the side length of the shorter side, because the shorter side is half the side length of the hypotenuse. And so if the hypotenuse is double, then this is going to be 16 times the square root of 3. You would just take 8 times the square root of 3 times 2. You wouldn't multiply both the square root of 3 times 2. You would just multiply one or the other. And then 8 times 2 is a lot easier, so we just write it as 16 square root of 3. Now this down here can simplify, so let's do this. Remember, when you take square root of 3 times the square root of 3, that's just 3. And so this has a side length of 24. So we found all of those side lengths. Now let's fill them in to our missing parts up here. So now let's figure out what the area of these are going to be. Okay, so for the area, there's 2 different ways to find the area, right? So you can set up 2 different ways. I want you to, if you haven't done this on your own, figure out what one way to find the area would be, and then come back to the video. Redraw this triangle or these triangles if you need to, but find one way to find the area of a triangle. Remember, the area of a triangle is just 1/2 base times the height. But depending on how you look at this triangle, there are 2 different ways to do it. So try this on your own and then come back to the video. Okay, so here's one way you could do this. It's just 1/2 base times height. So you could take 1/2 of the base times the height. So that's why down here, if you look at that, I have 1/2 AB times CD, where AB is your base and CD is your height. And so I wrote that down there, like this was 32 and this was 8 square root of 3. When I simplify that all the way down, I get area is equal to 16 times 8 times the square root of 3, or 221.7. So if you did it this way, see if you can't find the other way to set up this area, right? So here's the second way to look at this area. So the second way is to look at it like this. So here's your triangle, right here. Here is your base, so that's 16. Here is your height, that's 16 radical 3. So when we set this up, it's going to be the length of AC times the length of CB times 1/2. And so that's where this comes from. right? And then CA, that is 16. So this is going to be 1/2 16 times 16 times CB, which is 16 square root of 3. And so the area is going to be 1/2 of 16. So that's 8 times 16 times the square root of 3. And already you can see we're going to get the same thing, 221.7. So that's units squared. So these would be our final answer, regardless of which way you did that one. All right, so this is a long video, but there's a lot of good stuff in here. And that is it for 5.2. Analyzing triangles. And the did you know at the end of this about the scarecrow is kind of interesting. So take a look at that and tell me what you think.